Okay, so in this section we have been studying the order relation that we defined in the system of real numbers. Now we have already seen quite a few things, so let's continue with this next result. Here we are given a positive real number x. We have to first show that its reciprocal is also positive, and then if another positive real number y is given such that x is greater than y, then the reciprocal of x should be shown to be less than the reciprocal of y. That is, if you take reciprocal, the inequality gets reversed. So let's see the proof. Since x times the reciprocal of x is 1, we cannot have this equal to 0, and that is because x times 0 is equal to 0, which is not equal to 1. So the reciprocal of x cannot be 0. Also, it follows from that result that we proved in the previous part. Proposition 544. Please go to the statement of this proposition. That the product of a positive and a negative real number is negative. So x inverse, x times reciprocal of x equal to 1, this equation forces us to conclude that the real number x inverse cannot be negative, because if x inverse is negative, then since x is positive, by this proposition or by the consequence of this proposition which says that the product of a positive real number and a negative real number is negative, we would then get the statement that the real number 1 is negative. However, 1 we already know is a rational number, and hence by the embedding that we have got of the rationals into the reals, a real number also, and we know this is positive, so it is not a negative real number. Okay, so that thing is contradicted if we forcefully suppose x inverse to be negative. So it cannot be negative. Hence, by proposition 544, again another part of this proposition which says that the order relation we have defined in the set of real numbers satisfies trichotomy. That is, each real number is either positive or negative or 0, and exactly one of these three things is true for a given real number. So that means since x inverse is neither equal to 0 and nor is it negative, so it has to be positive. Okay. Now assume that y is a positive real number such that x is greater than y. We want to prove this inequality. Suppose that this is not true, then by trichotomy y inverse will be less than or equal to x inverse. Suppose, or let's just let's just suppose that y inverse is less than or equal to x inverse, and then we will arrive at a contradiction. Since x inverse and y inverse are both positive, we are still using something here. Yeah, proposition 547. We have by proposition 547 this thing. One can be written as x inverse. Okay. Now since it's given that x is strictly greater than y and x inverse is positive, so we can multiply both sides of this inequality by x inverse to obtain this. Yx inverse. Okay, so here what we have done, we have multiplied on both sides of this inequality by x inverse to obtain this inequality. We can do this because x inverse is positive, and that is coming from the first part of this statement, this proposition that we have already proved above. If x is a positive real number, then so its reciprocal, that is also positive. Okay, now you look at this inequality, that is our supposition. Since y inverse is positive, we can multiply on both sides of this inequality by y inverse. No, not by y inverse, but by y, because y is also positive, so we can multiply both sides of this inequality by y. Doing that, on this side we will have yx inverse, that will be greater than or equal to y inverse. And just like x inverse is 1, y inverse is also equal to 1. We have thus got one greater than 1. 1 is strictly greater. Note that here we have strict inequality. Strictly greater than 1, which is a contradiction, which again contradicts proposition 547, specifically the part of proposition 547 which says that the order relation on the reals satisfies trichotomy. So since we already have 1 equal to 1, simultaneously we cannot have 1 greater than 1. It's because of trichotomy we are having a contradiction. Thus, the last supposition above is not true. That is, we cannot have this. But then by trichotomy from proposition 547, X inverse must be strictly less than Y inverse. That's what we wanted to show. So this completes the proof. Okay. Now we have already seen that the formal limit of a Cauchy sequence of positive rational numbers need not be positive, need not be a positive real number. For instance, the formal limit of this sequence 0.1, 0.01, 001, etc. is the real number 0. So we already know this is a Cauchy sequence and all the terms in this sequence are positive rational numbers. But despite that, the formal limit is 0. So positivity of a sequence of rational numbers does not guarantee that the formal limit also has to be positive. But if we replace positive by non-negative, then the formal limit also has to be non-negative. And that is the next proposition. This is proposition 549. And it has a name also. The non-negative reals are closed This term closed is actually a technical term about which we will learn later. Let A1, A2, A3, etc. be a Cauchy sequence of non-negative rational numbers. Then the formal limit of an is a non-negative real number. Closedness roughly means that if we are considering only non-negative rational numbers, then we are trapped inside that non-negativity itself. So the system is closed. We are unable to go outside. A better explanation of this whole thing we will eventually see. Eventually, we will see a better explanation of this fact. The set of all non-negative real numbers is closed, and the set of all positive real numbers is open. These are some terms which comes from a part of mathematics known as topology. We will come across topology in our study of metric spaces in analysis 2 by Terenstra, the second part of this book. But for this, there is time C section 12.2. Now we will look at the proof of this proposition, and the proof is by contradiction. Suppose the formal limit is a negative real number. But what is the definition of a real number being negative? When do we say that a real number is negative? Precisely when the real number appears as the formal limit of a Cauchy sequence of rational numbers that is bounded away from 0 negatively bounded away from 0. Then there exists a Cauchy sequence Bn of rational numbers a Cauchy sequence Bn of rational numbers that is negatively bounded away from 0 and its formal limit is also equal to that real number, that is the formal limit of an. Thus, because this sequence is negatively bounded away from 0, there exists a rational number, a positive rational number such that Bn is less than or equal to minus c for all integers n greater than or equal to 1. Okay. That's what the definition of being negatively bounded away from 0 is. Also, since it's given that the original sequence, we lost the statement here. Anyway, the original sequence an is a sequence where each an is a non-negative rational number. So, an is greater than or equal to 0 for all n greater than or equal to 1. Hence, the distance between an and bn which is equal to an minus b. Do you see why this is equal to an minus bn? It's because an minus bn is a positive rational number. Why? an is already given to be non-negative, and because each bn is less than or equal to minus c, where c is positive, so each bn is negative. That means each minus bn is positive. So a non-negative an plus a positive minus bn gives us a positive an minus bn. Now an is greater than or equal to 0, bn is less than or equal to minus c, so minus bn is greater than or equal to c. This is equal to c, which is strictly greater than c by 2, and c by 2 is a positive rational number. Since c by 2 is greater than 0, we see that the sequences an and bn are not eventually C by 2 close. Not just not eventually C by 2 close, but in fact they are not C by 2 close at all. Why? Because the distance between an and bn is strictly greater than C by 2 for all n. So no chance of the two sequences being eventually C by 2 close. But then this just says that they cannot be equivalent. Thus, for them to be equivalent, they should be eventually epsilon close for every positive rational epsilon. But this particular value of epsilon has created problem, so they cannot be equivalent. Are not equivalent. But this contradicts this equality, because this equality directly says, the meaning of this equality is that an and bn are equivalent. So that means our first supposition is wrong. So our first supposition is wrong. That is, formal limit must be a non-negative real number. Okay. Now this result has a corollary which is quite useful. It's corollary 5,4,10. Let an and bn be Cauchy sequences of rational numbers such that an is greater than or equal to bn for all n greater than or equal to 1. Then the formal limits are also in that relation. Okay. consider the sequence an minus bn from the fact that subtraction of real numbers is well defined, we get the fact that this is also a Cauchy sequence, or you can do it in two steps. First, you consider the Cauchy sequence Bn, you take the negation of the sequence by negating each element of the sequence, each term of the sequence. It's easy to see, in fact we have done so by proving that the resulting sequence where all the terms are the negatives of the terms of the previous sequence, that is also a Cauchy sequence, and in fact using that sequence we defined the negation of a real number. And then we also proved that if we have two Cauchy sequences of rational numbers, then their sum is also a Cauchy sequence of rational numbers. So you combining those two things, this is a Cauchy sequence of rational numbers. We know that an minus bn is a Cauchy sequence. Okay. Also, since an is greater than or equal to bn for all n greater than or equal to 1, each term of this difference sequence is a non-negative rational number. Of this sequence is a non-negative rational number. So by the previous proposition, by proposition 549, the formal limit is non-negative. That is, this formal limit by the, we have already seen this. This formal limit is equal to the difference of these two formal limits, and this is greater than or equal to 0, which implies so this completes the proof of the corollary. And there is a remark after this about this greater than or equal to sign. In its place, if we have strict inequality, strictly greater than sign, then the result is not necessarily true. I mean result, of course the result is true, but because we make that change, so things will not work out. Remark 5.4.11. I am actually uploading a calculus video simultaneously, so I had to tend to it sometimes. Note that in the above corollary, the greater than or equal to sign cannot be replaced by the strict greater than sign throughout. Okay, that means if you change the statement of this corollary like this, an and bn are still Cauchy sequences of rational numbers, but an is strictly greater than bn, then you cannot conclude that limit of an is strictly greater than the limit of bn. And that can be seen with this example. For an equal to 1 plus 1 by n and bn equal to 1 minus 1 by n for all n greater than or equal to 1, we see that we already know, or it can be easily shown, that both of these are Cauchy sequences of rational numbers, and an is strictly greater than bn for this particular ans and bns for all n greater than or equal to 1, but their formal limits are equal and both of them are equal to 1. So one has to be careful in with this symbol. Even if we have an strictly greater than bn for all n, then also the result is applicable, because if we have strict inequality, that is also a part of inequality, but the conclusion will be this. In the conclusion you cannot write strict inequality. That is the thing you have to be careful about. This example shows that. Okay, we now define distance dx comma y equal to absolute value of xy in the set of real numbers, just like how we define the distance between two rational numbers. Distance, epsilon, closeness these things are defined for real numbers just like they are defined for rational numbers. In fact, proposition 437 and proposition 433 and proposition 437 are true not just for rational numbers but for real numbers as well. And the proofs of these facts are identical to the proofs of the corresponding facts for the rational numbers, since the real numbers obey the same laws of algebra. As the rational numbers. Same laws of algebra and order. Technically speaking, both the system of rational numbers and the system of real numbers are examples of something called an ordered field. So they are exactly alike. And the properties of these systems that depend only on the basic properties of an ordered field will be true in both the systems. Naturally, because the properties are exactly alike. We now observe that though positive real numbers can be arbitrarily large or arbitrarily small, but they are restricted also in some sense by rational numbers and integers, positive integers. Though they cannot be larger than all the positive integers or smaller than all the positive rational numbers. That is the content of the next result. Bounding of reals by rationals. So this is proposition 12. Let x be a positive real number, then there exists a positive integer and a rational number. Let's write the rational first. In fact, a positive rational number. Q such that Q is less than or equal to x. No matter how small you choose x to be, you can always find a positive rational number that is either equal to x or smaller than x. Also, there exists a positive integer n such that x will be less than or equal to n. Okay. Proof. Now before I write the proof, let me just see what the situation here is with the upload. Give me a moment. Okay, so the upload is over. I mean the processing is over. We will do it after this video. So where was I? I wanted to prove this. Okay, since so the thing we are given, the hypothesis is that x is a real number, but it's a positive real number. So that means it will be the formal limit of a Cauchy sequence of rational numbers that is positively bounded away from 0. Since x is a positive real number, there exists a Cauchy sequence. It's better to mention that. Cauchy sequence of rational numbers that is positively bounded away from 0. And its formal limit is x. Now since it is positively bounded away, so then there exists a rational q greater than 0 such that q is less than or equal to an for all n greater than or equal to 1. Okay, so x being a positive real number has led to all of this. The next thing we will use is that an is a Cauchy sequence, and we have already proved in the section on Cauchy sequences that such sequences are always bounded. We will use the boundedness here. Since an is a Cauchy sequence, the exact result is lemma 5.1.15. Implies an is bounded that is there exists a positive rational number C such that an which is equal to absolute value of an. Why? Because this is a sequence that is positively bounded away from 0. So in particular, all the terms in this sequence are positive real numbers. So any such term will be equal to its absolute value, and by the definition of boundedness, this will be less than or equal to C, and this will be true for all n greater than or equal to n. Now by yet another result, which is proposition 441. There exists it's that result which tells us that every rational number has an integer part, that result. Now by proposition 441 there exists an integer n such that n is greater than or equal to c. C is a rational number, so n is equal to c or greater than c. Such an integer can always be found. Since c is greater than 0, because c is a positive rational number, n is a positive integer. So what do we now have? Taking everything into consideration, we now have q less than or equal to an, which is less than or equal to c, of course, but that's not what we need. We need n, because n is greater than or equal to c. Now this is a place where we can use the corollary. That corollary 5, 4, 10, for all n greater than or equal to n. Thus by corollary 5, 4, 10, so corollary 5, 4, 10 tells us that since these three are Cauchy sequences, an is a Cauchy sequence that is given to us, q is a constant sequence, q of rational numbers, so that is also a Cauchy sequence of rational numbers. N is a constant sequence of integers and hence rational numbers, so that is also a Cauchy sequence of rational numbers. So we can take formal limits of these sequences and they will maintain the same inequality. Limit of q is less than or equal to limit of an, which in turn is less than or equal to limit of n, or limit of q is q, limit of an is x, and limit of n is n. So this shows that if we have a positive real number x, then that is bounded from below by a positive rational number and bounded from above by a positive integer. This completes the proof. Okay, now this result has an important corollary which has a name also. It's called the Archimedean property. So the things we are going on proving, these are some most basic fundamental facts about the order relation in the system of real numbers. Let x and epsilon be any two positive real numbers, then there exists a positive integer n such that n epsilon is strictly greater than x. This is the Archimedean property. So let's first see the proof and then we will say something about the significance of this property and why it's important. Consider the positive real number x divided by epsilon, because x and epsilon are both positive, their ratio, their quotient x divided by epsilon will also be positive. Then by proposition 441, oh, not proposition 441, why should we go there? And in fact proposition 441 cannot be applied here also, because the number x divided by epsilon is not a rational number, it's a real number, so we have to use this part. So by the previous proposition, that means 5, 4, 12. There exists a, I think in the original statement we have m here. There exists a positive integer n such that x divided by epsilon is less than or equal to n. Taking m to be equal to n plus 1, we have this is strictly less than m, or m epsilon is strictly greater than x. So this completes the proof. Now the significance of this result is this. Note that says the following. If x and epsilon are positive real numbers, then no matter how large x is and how small epsilon is, we can always, or if we keep adding epsilon to itself, then we will eventually overtake x, because since m is a positive integer, so m epsilon is epsilon plus epsilon plus epsilon, m number of epsilons have been added. This result, the Archimedean property says that even if x is extremely large, say 10 to the power 100, and epsilon is extremely small, say 10 to the power minus 1 billion, that small, still there is a positive integer m so large that if we multiply m with epsilon, then the product will be greater than x. So you just keep on adding epsilon, the results will accumulate, it will increase, the sum will keep on increasing, and at some stage the sum will exceed x, and it has important consequences. And lastly, there is one result which says that the among the real numbers, the rational numbers are densely situated. Between any two real numbers, we can always find a rational number. Whose proof, however, we will see in the exercises only. So this is proposition 5.4.14. Given to real numbers x and y with x less than y, there exists a rational number q such that x is strictly less than q and q is strictly less than y. For the proof, see exercise 5. Okay. Okay, now some closing remarks of this section. We have now completed our construction of the real number system. This number system contains the rational numbers and has almost all the properties of the rational numbers. For example, it has the arithmetic operations, all the four operations of addition, subtraction, multiplication and division. The laws of algebra, which are exactly similar. In short, we say that both the system of rational numbers and the system of real numbers are fields. And the laws of order, they are also similar. For example, we have trichotomy. Any two rational numbers are either equal or exactly one of them is greater than the other. Similarly, any two real numbers are either equal or exactly one of them is greater than the other. Or those laws that involve both order as well as some arithmetic operation. Namely, if you have x greater than y and z is a positive number, then xz is greater than yz. This is true if x, y, z are rational numbers and also true if they are real numbers. So far, although we have created a new system of numbers which contains the rational numbers inside them, and it has numbers which are not rational, that those numbers are also there. It's a larger system in which the system of rational numbers is sitting inside as a subsystem, and it satisfies almost all the properties that the rational number system has. But what is the advantage of doing all these things? We now come to that issue. However, we have not yet demonstrated any advantage of the real numbers over the rational numbers, even after so much effort. We have just managed to show that the system of real numbers is at least as good as the system of rational numbers. So it seems that all of our efforts went in vain actually. But that's clearly not the case, because otherwise we won't be doing it. So far things have been going smoothly. I mean, we hit a little snag here and there. Namely, for example, when we tried to define the reciprocal of a real number, we could not do it in a straightforward manner. We had to devise the concept of sequences bounded away from 0. Then, while defining positive and negative real numbers, we had to devise those concepts of sequences positively bounded away from 0, negatively bounded away from 0. So we have actually gone through those obstacles, we overcame them, and we have produced a larger system. But it turns out so far that it's just as good as the rational number system. If that is the only thing, then this is really useless. But fortunately, that is clearly not the only thing, because in the next few sections we will show that the real number system is actually superior to the rational numbers and is a system that is particularly suitable for doing analysis, to carry out limiting processes without bothering whether limits will exist or not. But in the next few sections we will show that the real numbers can do much more than the rational numbers. If you recall, in the system of rational numbers, this equation has no solution. Now, in the using the language of real numbers, it's the same as saying that the square root of 2 is not a rational number. But now in our larger system we can define square root of 2. In fact, we will prove existence of square root of 2, and not just that, we will prove the existence of nth roots of any positive real number, where n is a positive integer. And these things are not possible in the system of rational numbers. And many more things are doable in this larger system. For instance, in the real number system, we will be able to define square roots. Just to give you a simple example. And finally, there is a remark about something which we have neglected from the very beginning, and we have been neglecting. We will come to that, and it's the fact that the real numbers can be expressed using the decimal system. So this is the last remark. So let's see this remark and end the video here. 5, 4, 15. Up until now, we have not addressed the issue or the fact that the real numbers can be expressed in the decimal system. For instance, the formal limit of the sequence 1.4, 1.41, 0.414, etc. is conventionally written as this. We will address this in an appendix, in appendix B. But for now, let's just remark has some subtleties. For instance, are in fact the same real number. So with this, the text part of this section ends, section 5.4. After this, we will move on to the exercises, and there are two more sections left in this 5th chapter, which treats all the things about real numbers. In the next section, which discusses the least upper bound property, there is something known as the least upper bound property or supremum property, that the system of real numbers has, which is not there in the system of rational numbers. So this is where things deviate, and this is the property that is the single most important thing about real numbers, and which makes the system of real numbers so useful, and it also makes it a line, a continuous line, a real line, unlike the system of rational numbers, which is not a continuous line. It has points on the line, but there are gaps. For example, where square root of 2 should be on the line, the rational number system has nothing. So it's the lack of those points that makes the system of rational numbers unsuitable for doing analysis. Because in analysis we are doing limiting processes, we want to end the limiting process somewhere. Okay, now if that somewhere is not available at all, then what can you do? Such a system is ill-equipped to handle those type of things, those type of operations or processes. So that is the main reason for jumping from the system of rational numbers to the system of real numbers. And once we see what least upper bound property can do, then in the final section of this chapter, this is 5.4, no, so 5.5, in 5.6 we will use all those things to handle exponentiation in the system of real numbers, that is in its full generality. So with that I end this video. If you have any doubt regarding these things, you can always comment in the comment section. I would like to be able to try to answer those things. And one more thing is that these videos should not be considered as classes or lectures, because I am also simply a student like you people. I am not a university professor. I don't want to be. I just want to continue to learn about these things and find out many things. I am not an expert in any of these areas of mathematics. I am vigorously trying to learn these things with you all. So these videos should be treated as a discussion, and the discussion will happen only when you ask me questions and only when we interact in the comment section. So if possible, please do that. And so that's just it for tonight. So signing off, this is me, Lucifer, from a mathematical room. Have a nice night.